All right, line A1, we're taking a look at learning task number 15, which is where we are now going to start to examine our inductors as they operate inside of an AC circuit. This is once again really critical that you identify for yourself that this is AC we're talking about now, which means that we're going to have a little bit of a different overall effect that we'll get out of the inductors. They're going to operate a little bit different, but they're still going to rely upon their base description that we had of them, which is that any inductor is going to go and opposes a change in current by using voltage. A couple of things that I want to point out about this saying over here. First of all, it doesn't oppose current. What it opposes is a change in current that we are going to go and see. We know that in a DC circuit, if we got flatline DC circuit and we bring an inductor into that, that inductor is going to go and oppose the current when the current is first brought in, when the current goes up, or when the current goes down. But once we're at a steady state current, the inductor basically steps back out of the circuit. It opposes any sort of a change in current. And the way that it does that is it's going to go and use voltage. We use that analogy of the little linebacker. And that the little linebacker is going to be our counter EMF that we are going to go and generate that is going to slow down the rate of rise of voltage that we would normally otherwise get out of our inductor. The big thing is that now we're working inside of AC, which means that current is always changing, right? We don't have any point along an AC sine wave where we can say that current is not changing. It is always changing as we're going along there. Therefore, we're always going to go and get inductive reaction. And what does it do when it sees changing current? Voltage. It is going to go and be dumping out counter EMF, an opposite voltage, at all times because it is constantly seeing that changing current inside of here. So with that as our groundwork, let's take a look at our AC circuits. What we're going to do is we're going to start by examining a purely theoretical inductor. Now we know that an inductor cannot be built without the use of wires. But it's far easier for us to start with a theoretical one, and then once we've established what happens inside of the theoretical one, then we'll go into the practical and how that actually affects, the power factor, the phase angle, and all the rest of that. So just bear with us on this explanation. We will deal with the practical AC inductors as we get there. First thing that we did take a look at over here is that we've only got a single source, we've only got a single load, and therefore we know that what we must have is all of our voltage must be dropped. According to Kirchhoff's law of voltage, the voltage dropped on the load must equal the voltage sourced over here. What do we drop volts across? Well, if it's a purely theoretical inductor, the only thing that we can drop volts across is the counter EMF, CEMF, or the opposite value of voltage. In other words, we're going to go and have a vector that is going to be established over here, my source, and we're going to oppose it with another vector that's going to be 180 degrees out of phase, a voltage in the opposite direction, and that's what's going to be slowing it down. Ultimately, this one is going to go and win, our source. It will overpower, but this one is slowing it down, that counter EMF. They give us a set of graphs over here. Now, a couple of things that I do need to go and point out. First of all, this is a stabilized graph. It is 100% been stabilized. This is a couple of cycles in. This is not the instant that we are applying power to an inductor for the very first time. If this was the instant that we were applying power to an inductor at the very first time, our current would have to start at 0 along with our voltage, and then we're going to kind of see this little bit of a wobble until it snaps into the rest of what we got going on over here. Because that only happens the first time that we power one of these on, we don't need to worry about it, okay? Just work with the fact that right now we've had our voltage applied for a couple of cycles at a minimum, and so we've got a stabilized system, because then we can start to go and analyze everything that's happening inside here. The other thing that we need to go and take a look at is, what does an inductor oppose? It opposes change in current. So we know that counter EMF has got a formula. E is equal to negative L delta I over top of delta T. Remember, that's that formula that was missing all the deltas earlier? This is going to be a formula for counter EMF. We know that counter EMF is going to be a vector opposite of our applied. So if this is our E applied, start the thing in orange, origin over here, our E applied is going to be going in one direction, and our counter EMF is going in the opposite direction. As my applied increases, my counter EMF is going to go and increase as well. That's what we're seeing on here. Is we're seeing two main waveforms. We'll identify them. This is going to be my applied voltage waveform. That's the AC that I'm applying to the circuit. This one over here is going to go and be my counter EMF. It's going to be the opposition, the baby linebacker that is being created by this one over here. So, since this counter EMF has been generated by that, and since that is all generated through this formula over here, we can now mathematically go through and prove why we've got this weirdness that's happening off of our current. Because if you take a look at our current, it is no longer going to be considered to be in phase with my voltage inside of here. Here's why. This formula is highly, highly dependent upon delta change, right? The change in current. Delta I over top of delta T that we are going to go and see. So any place where my current is going to be changing, that's where I'm going to go and establish my maximum values of voltage. Where am I going to go and have the most change? Well, the most change, if I were to examine the blue line over here, this current line, change just refers to rate of change over top of rate of time. So if I were to go and split these two lines and compare those to these two lines, I would see that over the same amount of time that this current level has varied only a tiny, tiny bit, whereas this current level over here has varied a lot, right? We see our greatest change in currents right over here on any sine wave, where that sine wave is crossing over my x-axis as we're going through there. Which would mean that if that's where I get my greatest rate of change, right over here, that would also mean that's where I would be establishing my greatest counter EMF at that point. And we see that that lines up. This delta I lines up with my maximum rate of change that I'm going to have over here. What about when we get to the very peak of this? Well, when we get to the very peak, just for a fraction of a split second of a fraction, we are going to go and have no change, right? If you zoom in on any curve close enough, eventually it's going to appear as if that curve were flat. Well, what is my change in current over top of a change in time? That would mean that at that point, it would be at a value of 0, which would mean that my voltage would also have to be at a value of 0. And so over here, if I take a look at that, my change in current, delta I, is going to be at an absolute minimum, is going to be at a 0, which means that my voltage, my counter EMF, that's this dotted line that we're developing off of it, is also going to be at a 0 over here. Couple more things that we can analyze out of this one, so we'll just add in a couple more dotted lines over here. This is going to be delta I, we get maximum delta I. This one over here, we're also going to be looking at the top of that one there, another delta I that we are going to go and have over there. So change rate of change of current. If I take a look at my counter EMF over here, I see that my current is rising from a negative value to a positive value, right? We go through on time. So if I look at this, it is going to be a positive delta I that I'm getting here. So I'm just going to assign that. If I've got a positive delta I, and I put a positive delta I into this formula that has got that little negative that we got down there, a positive times a negative equals a negative, and that's why we get a negative counter EMF that I'm going to have out over there. Over here, I don't have either. I've got 0, right? Because this thing is going to be flatlining at the top of the curve over there. So it's just going to be at a value of 0. And then right over here, I see that I'm going from a positive value down to a negative value over here. So it's going to become a negative delta I. So it's a negative delta I. If I've got a negative delta I multiplied by a negative, that's part of my formula over there, negative times a negative, it's going to go and give me out a positive that I would have, which is why my counter EMF is going to be positive over here at that point. That's about as far in depth as we need to go off of this. Everything from this corresponds to delta I over top of delta T. We have to go and build, the only opposition inside of our circuit would be for us to go and use counter EMF. Therefore, our counter EMF would have to look like this, and for us to establish this type of value of counter EMF, we would need to go and have a steeply positively changing current. For us to get a counter EMF of 0, we'd have to have 0 For us to be having a positive counter EMF, we'd have to go and have a negative steeply increasing current, etc. This graph that we have over here is going to be for a theoretical AC inductive circuit. It is not a practical circuit. It's not one that we're going to go and see on a day-to-day basis because we're always going to go and have a little bit of resistance inside there, and that's going to have its own little bit of jankery that we are going to go and have inside of there. We'll cover that as we get there. We have got only one more thing to go and do, and that is to define our relationship. If we take a look at these two waveforms, if we want to define lead and lag on a waveform, first of all, we have to make sure that they are the same frequency. They are. My current is going to be the same frequency as my voltage. Then I find a place where they're doing the same thing in the same direction. Over here is where I'm crossing my x-axis in a positive direction. Over here is where I'm crossing my x-axis in a positive direction. And then I just go and say, well, which one of these crossed the x-axis first? Well, this one crossed all the way at 0. That's my applied voltage. This one crossed over here at 90, right? 90 degrees later. So therefore, I would say that this one is going to be lagging. My current lags the voltage. I can graph that like this. Remember that whole thing about 4-quadrant graphing that we can go and graph? When we were dealing with lead lag, we said we never want to cross that line, that 180 degrees. Right now what we're going to do is we're going to use our applied voltage as our reference vector, so we place it along the 0 axis. And if I need to have current that lags by 90 degrees, that means that that current would have to be facing down like that. That's going to be our phasor representation. It's called a phasor because it is always changing, because it's AC, it's rotating around. But it shows the relationship between our volts and our current. We are going to go and use the term Eli. Okay? Eli happens to be the name of the cat that you see popping up inside of videos here, running around, sitting on top of me and stuff like that. He's the one that lived in the garage before I invaded here to go and teach out of here for COVID purposes. Eli is going to be our mnemonic, which is a memory trick, to go and remember what it is. First of all, if I take a look at the center letter L, L stands for inductors, Henrys, right? That's just what we have. And if I take a look at this, I see that my E, which is my volts, and I see that I, which is going to be my amps, right? We see that my voltage leads the current when it comes to a inductive type of circuit. So we're just going to use that term Eli to remember my inductive types of circuits. All right? Beautiful. Okay, let's talk about inductive reactance then. Inductive reactance is something that's brand new for second year. We have not covered it inside of first year. It is going to be defined by this. XL is equal to my EL divided by my IL. What are all these subscript L's over here? These subscript L's are to do with the fact that it's over top of an inductor. When we have got an inductor in place in a circuit, there's something that prevents us from going into out-of-control current. And that thing that prevents us from going into out-of-control current is simply going to go and be all of those magnetic lines of flux that are going to be stretched around there, right? It's like blowing up a balloon or stretching out an elastic band. It gets harder and harder to do it as you stretch this thing out further and further. Because of that, we know that there's some sort of feedback or force that's being pushed back into that system. That's what's preventing this. Now, we can't really just quantify it off of magnetic lines. We could, and there are formulas to go and do it, but those are physics formulas that we don't really need to use for our day-to-day analysis of that. That's for people that want to, work at doing the deep dense theory that involves transformer windings and things like that. We just need a way to go and say, hey, I want to quantify this opposition, the stretching, the magnetism fields that we have over here. I want to quantify it into something that I already know. And so we're going to form this new thing that's going to be called my XL. XL is the effect of an inductor on a system that acts like resistance. It is not actually resistance. Resistance is R, defined by K times L over top of CMA, physical components. XL is going to be defined by what's happening inside of our circuit, the amount of current that I'm letting through based upon the amount of voltage that I'm going to go and be applying to it. So we use the same formulas as what we would do for Ohm's law, because it's a form of resistance, and XL is actually going to be measured in ohms XL. Once again, subscripts are going to be very, very important we're going to have XL. We're going to also have XC for capacitance later on. So we need to make sure we keep these things straight when we're writing them on exams, because a straight up ohms means resistive ohms. An ohms X could be inductive or capacitive later on. Let's talk about the factors that affect the amount of opposition that we are going to go and have. Voltage. If we affect the amount of voltage that we are going to go and have, what that's going to do is it's going to go and change the rate of current change. It's going to have to double that rate of current change, which means that we're also going to go and get double our peak current. And so really we end up with both our volts and our currents that are going to go and change together. So changing our value of voltage does not affect the XL of an inductor. I'm going to actually go to this slide over here for that one. XL, volts, not affected by the volts. Frequency. The frequency makes a big difference to us, because if I go and double my amount of frequency, that means that my waveforms, instead of looking like this, are now going to be looking like this. And if I take a look at that, that is a far, far more steep side to it, which means that my rate of change is also going to be doubled up, right? Where it's going to go and change way, way faster. So if I'm going to go and have this, doubly fast that I'm going to go through there, yet I'm still got the same amount of peak voltage, then I'm going to also affect the amount of current that I'm going to have going through it. The problem is that this current is now only happening over top of half the amount of time. Before, I had this whole slope that took, all the way up to here. That's how long it took. Now we've cut that time in half. Once again, if I go and take a look at my formulas, E negative L delta I over top of delta T, what I'm going to go and see is that I am going to go and have halved my change in time, right? The current stays the same. The L stays the same for that one, but I'm going to have changed the amount of time that I have to go and react. And because I've changed the amount of time to go and react, my inductance, my XL, my inductive reactance, is going to go and double, because I'm just going to be clamping down. I've got the same inductor, I don't have the same amount of time to get stuff done inside of there. So frequency is going to go and be a direct relationship. My actual inductance, the L value that I'm going to go and have to this one. If I go and take that L value and I double it, and I work off the same counter EMF formula, E is equal to negative L delta I over delta T, then what I'm going to have, if I'm going to still maintain the same value of voltage, I would have to go and decrease my delta I over top of delta T, right? If I double the L, half the delta I, that way I can maintain the same E. Which would mean that my peak current is also going to go and decrease. And if current has decreased, that simply means that there is more opposition to current flow, more reactance that I'm going to go and have. All of this is going to go and make a difference inside of here. So my L and my F both are going to make a difference inside here. What we do is we combine this all down now into a single formula that says XL is equal to 2 pi F L over here. We see that the L is directly related, so if L goes up, XL goes up. If L goes down, XL would go down. If frequency goes up, XL would go up. If frequency go down, XL would go down. And then the last part that we have over here is 2 pi. 2 pi is not something that we generally use a lot inside of electrical. We'll see it in a bunch of formulas, but we don't do the deeper analysis of it. What 2 pi is it is dealing with the radians of a circle. Or in other words, how far around. It's a rotational type of thing that's going to be happening. We, generally speaking, are going to deal with dividing our circles down into degrees, not into radians, but radians is just another form of splitting apart a circle. And when we're dealing with radians, each half of a circle is going to be defined by a single pi. So a single pi for that one, as well as we're going to have a single pi for that one, which means that if I've got 2 pi's, that defines an entire circle. So anytime that you see this 2 pi, that just means that we're looking at something over top of the entire 306 degrees, or over top of the entire sine wave that we are going to go and have. It indicates that there's something sinusoidal or circular about it. This is going to be a very important formula for us to go and remember, because our XL is going to go and change based upon what our frequency is and based upon what our inductance is of the actual physical components. Okay, so if we've got XL and if we've got current, how is that going to go and affect our total amount of power? Well, here's where we're going to get into some really cool and funky power. This is going to be that same graph that we started out with, this one over here, where we had the applied value of voltage, we had the current, and we saw that we had our counter EMF. Now what they're doing is they're superimposing a third one over top. They've taken away the counter EMF one. They're showing here's my applied value of voltage, here's my current, 90 degrees lagging from here, and then they're showing that now we get this new waveform, which is going to be this blue one, which is going to be a power type of waveform. This power waveform that we're seeing is going to be power that is developed from my inductor. And it's really funky, because when I take a look at it, over here I see I've got, well, first of all, let's go with the formula. Watts is equal to E times I, my current times my voltage. If I take a look at it, I got a positive E and a negative I, so positive times a negative means that I'm going to have a negative value of power. But then right over here, I got a positive I and a positive E, so I'm going to go and have a positive value of power. And then over here, I've got a positive I and a negative E, so positive times a negative means I'm going to have a negative value of power. And then over here, I'm going to go and have a negative current and a negative voltage, but a negative times a negative brings me out to a positive once again. And what I get is I get this power waveform that is going to go and take power, and then it is going to go and feed power back in. And it becomes useless, quite honestly. It's like you taking $100 to the bank. If you take $100 to the bank today and you put it in, that's good. You saved $100. If you take $100 tomorrow and you put it in, that's good. You saved another $100. You come in the next day, you put in $100 in, it's good. You've saved $300 because you're always doing something in the same direction. But if you go to the bank, back in the days when you could kind of go to a bank instead of having to go to a bank machine, let's say you stood in line and you took out a $100 bill and you passed it to the teller, and you said, I'd like to deposit this, and they did the paperwork, hit the stamp, etc. And you say, I'd like to withdraw $100, they would give it back to you. And then you say, I'd like to deposit this $100, and they would deposit again, and you withdraw it again, and they would get very annoyed, and so would everybody else that's waiting in line, because what you're doing is absolutely useless. It's a waste of time. You're taking something, and then you're dumping it back in. That's what this type of power is doing to our electrical systems. It's annoying. It's going to be what we refer to as our VARs, or volts amps reactant, that we are going to go and have. We've got two types of power here. This one would be true power that we would be taking into our circuit. So we're taking this power in right now. We're using that to go and expand our magnetic fields outward around the inductor. And then right over here is where we are going to be collapsing those same magnetic fields back inwards. And as we're doing that, then that's, pushing that power back in. So this is where we're taking from the source and we're delivering back to the source. Once again, it's a stabilized waveform. They don't show the first couple of wobbles as this thing sets itself up, but it's really just a useless form of power. It is still current and it is still power, because we're still having to go and take, that whole process of you handing that $100 bill to the teller and handing it back. At the end of the day, nothing effective has been done. You've wasted your time, you've wasted their time. But your arm would be tired from taking that $100, passing it over, and pulling it back through. We have, inside of a reactive type of circuit, we have got current that we're going to go and remove from the supply, and then we're going to send it back in. We can actually send power back into a supply. It's 100% legit. It just gets diverted then out to other loads. So we're just taking current back and forth. As this current goes through our system, it does create other losses. And it's, it takes up system capacity, because I have to go and use, this certain percent of my system to deliver this current and send this current back that I'm going to have to reserve for it. We don't want to go and have a lot of this power. We call it reactive power, sometimes referred to as wattless power, and other times it is going to be referred to as quadrature power. Quadrature, wattless, VARs, any one of those are going to go and work. What we're generally speaking going to talk about is we're going to go and use the term VARs. And once again, we're going to have to make sure that we subscript it as being VARs L, or VARs lagging, that are going to go and be inductive. They are a lagging type of VARs, because if I take a look at it, when I'm taking them from the supply, I'm taking them out, or sorry, when I'm doing the power, the actual taking of power from the supply, it's behind my voltage once again. Just remember, keep it the same as what we have for our current. Our current lags the voltage in an inductive circuit, so does our power inside of these. Okay, last little bits that we have over here for inductors in AC just deal with when I've got inductors that are specialized. And it's going to be dealing with actual inductors. There's a little short brief where they start talking about the Q. The Q of a coil is just going to be the quality factor of a coil. It's going to be a ratio of its inductive reactance to its resistance. We did cover resistance and reactance before, right? XL and R. Back at the very beginning of this course, we just started into some simple triangles, and we did some triangles, and one of them was an impedance triangle, where we had R, XL, and then we had that Z on there as well. Q factor is going to go and give us R and XL. So if I've got Q factor, the other thing that Q factor tells me is it tells me the tangent of whatever that angle is, or of that component. We'll deal with that stuff later on. Just know that the Q factor is a tangential type of relationship. There is also the concept of non-inductive coils. Back in level 1, you would have covered, resistors, carbon, compacted resistance, metal film resistance, things like that. And then they would have also talked about wire-wound resistors, which are going to be our most stable and our heaviest duty and one of our most accurate types of resistors. For us to form one of those, if we're going to wind it, what we do is we take the wire and we fold it in half. You're seeing that right over here. So I'm going to take a length of wire, it could be like 3 meters of wire. I'm going to fold it in half, and then I'm going to go and wrap that around. And what that does is that means that any current that's being fed through is also going to have to come back in the opposite direction, which means its magnetic fields are going to cancel each other out, which means that I'm not going to get any sort of N squared. You remember the whole formula for inductance? L is equal to N squared mu A all over top of little l. I'm going to have 0 turns squared because these ones are going to be counteracting each other. These turns basically take each other out, which means that I'm going to end up with 0 inductance. There'll be a tiny little bit of inductance, but that's going to be no different than if I had a straight piece of wire that I would have off. It's a very common thing to do to go and block out magnetic signals by taking wires and folding them in half. Now they bring it up over here for the non-inductive resistor. Later on, you're going to go and cover instrumentation inside of your 4th year. Not actual instrumentation all the way through, but you're going to cover, how we deal with sensors and things like that. And we've got a lot of small sensors that when we buy them, particularly for some things like load cells that are used for industrial weighing, you can get load cells that you place underneath a bunch of steel beams. You can weigh cars and trains and all sorts of fun things with them. Those load cells that we are going to have conductors that are going to be parts. They're going to be measured as being part of it. It's a very small amount of current that's going to go through what we refer to a Wheatstone Bridge. And then that Wheatstone Bridge, the way that thing goes and sets out a value of voltage, and we'll measure that voltage value across the center of the Wheatstone Bridge, that's what's going to go and tell us how far we've distorted our beams. They're also called bonded metal strain gauge. The wires that come out of here are going to be long, but you're not allowed to cut them off. Most load cell manufacturers straight up outlaw it because it changes their readings. So instead, what you need to do is you need to go and bundle them tightly. What you'll see electricians who don't know what they're doing, they're going to go and take them, they'll wind them into a nice little coil, they'll stick a tie wrap around it. And then here's the load cell. It keeps it out of the way. Yes, it's neat, but electrically they have just formed this thing into an inductor. We use the same concept as what we see here on the wire-wound inductors anytime that we would be dealing with instrumentation cable. We've got our cable, we'll run it all the way along, we'll work a loop towards the middle of it somewhere. So somewhere over there you got a loop, and then you're just going to take that loop, you're going to push it out, you're going to fold it in half. Not tight, you don't want to crimp it with your pliers or anything stupid like that. But once you get this thing folded in half, then you take this folded set of wires and then you start coiling that folded set of wires up. And that way you've got cancellation of all flux and you're not going to be creating any sort of inaccurate measurements out of them. The last section that they talk about as well is what we refer to as a saturable reactor. Saturable reactors are a way that we can go and use the magnetic domains inside of a component to go and lock down the amount of inductance that I'm going to go and have. L is equal to N squared mu A all over top of little l. And we talked about how we can have variable inductors before. This is a form of variable inductors. Because what we're going to do is we're going to affect this mu, this permeability that we're going to have. And the way we do it is we just pass current through our DC coil. If I go negative, positive, like this, what it's going to do is I have current that comes in, goes around like that. So you can go and use your left-hand rule for coils, and you should find that you got a north over there, which would mean that this is going to go and set up magnetic lines going through like these. If I set up magnetic lines, those magnetic lines are going to lock down the magnetic domains inside of my ferromagnetic material, which means that I'm going to go and lose permeability inside of here because I've got domains locked down. I've got lines of flux that are already blocking up some of the space. It's no different than anything else, that you might have space for, whether it's going to be, freeways or hallways. If a bunch of the lanes are blocked up, you got less room to go and maneuver. And so for my AC coil, if I take a look at the AC coil, which is going to be this one, all the way over here. Note there's a single wire in and a single wire out on these ones. I'm going to be able to lose permeability. If I lose permeability, if this DC coil starts to go and saturate, I'm going to lose permeability, which means I'm going to go and lose my L. Now if I lose my L, XL is equal to 2 pi FL, I'm also going to be able to go and drop my XL, like that. So I can go and use this DC coil here, a tiny, tiny little bit of current through the DC coil. Let's just stick lots of turns around it, which is then going to give me lots of Webers, right? You should remember this formula. Webers is equal to my ampere turns. So if I have lots of Webers of flux locked down inside of here, I can use that to go and adjust this, cut out some permeability, drop that L. If I drop that L, I'm going to drop that XL, which means that I'm then going to allow more current through this coil because the XL of that coil will have dropped. We'll use them in all sorts of places where we need to control large amounts of AC current, but we want to go and control it in a just using electrical, where I'm not having to go and physically move variable resistors or anything like that back and forth inside.